Assalamualaikum warahmatullahi wabarakatuh. My name is Nursyamimi binti Zahri. My matter number is 1212973. My topic for today is a review of influenza infected cases using SIR model. In this assignment, I talk about the problems that come up because of how quickly influenza spreads, focusing on how common it is and how bad the effect can be. According to the Centers for the Disease Control and Prevention, influenza viruses mostly hurt the lungs. The SIR model, which is a basic tool to divide communities into groups of people who are susceptible, infectious and recovered. This helps us understand how disease spread. For problem statement, the problem statement focused on analyzing influenza transmission using the SIR model, aiming to understand spread, intervention, impacts, and herd immunity. The discussion acknowledged SIR model limitation and aims to explore adaptation for better accuracy. Tolles and Luong study emphasized that SIR model's role in assessing influenza vaccination effectiveness, considering seasonal patterns and human behavior. The model informs decisions on intervention like school closures and antiviral treatments. However, this article underscores that SIR model limitation and emphasized the need for modification to enhance real-world applicability. For methodology, this study used the SIR model for ordinary differential equation and mathematical analysis. It supports the idea that flu vaccination can lead to disease loss. This study examines individuals who have been sick with influenza and recovers. Secondary sources include books, websites, and research journals. Overall general equation is S plus I plus R is equal to 1. The movement of individuals between compartments is governed by a set of differential equations. The S over dt stands for rate of change in the number of people who are susceptible. The I over dt is the rate of change in the number of infected people based on how quickly susceptible people become ill and how quickly infected people become better. The R over dt stands for rate of change in the number of people who have been recovered. And a few factors are what the SIR depends on is beta. The beta is the transmission rate, which is the average number of new cases that one infected person causes. For gamma, recovery rate, which show how quickly sick people gets better. Based on the slide, the first equation shows that the characteristic of the sensitive group change over time. We can guess that the rate of change will be negative starting with a weak population of 1 and going down over time. The rate of change is based on the number of contact B, and more contacts mean a faster rate of change. This rate of change is based on the current population of people who are susceptible and infected, not on the population that has healed. The second equation shows how the number of sick people change over time. It has two words in it. There is no change in the sign of the first number. It is the number as the right-hand side of the last equation. It means that there are more people who are sick. The second word is negative, which means that fewer people are affected. The last equation shows how the restored population has changed over time. The last number in the equation is the same as the side on the right. My initial data that I use is at t=0. Since the initial infected population needs a tiny non-zero figures, we will set it to 0.0001 and we will begin at 0.9999 for the sensitive group and everyone else who is not affected. Furthermore, 0 will be the initial restored population. This graph illustrates the individuals who were susceptible, infected and recovered respectively as predicted by the SIR model. When R0 less than 0, each person who contracts the disease will infect fewer individuals, so the outbreak will gradually disappear, and the L over dt more or less than 0. Similarly, when R0 bigger than 1, each person. This graph illustrates the individuals who were susceptible, infected and recovered respectively as predicted by the SIR model. When R0 lesser than 0, each person who contracts the disease will infect fewer individuals, so the outbreak will gradually disappear, and the L over dt fewer than 0. Similarly, when R0 bigger than 1, each person who gets the disease will infect more individuals Thus, the epidemic will spread and the L of t bigger than 0. For the discussion, for t, I change it to 1 to 6 days with the parameters beta is equal to 0.15 and gamma is equal to 0.079. At the beginning of the curve, susceptibility are high, and by the 61st day, they begin to fall as individuals become infected with the virus. In the beginning, the shape can provide information about how rapidly the virus spreads. The infection curve begins at a low level and begins to increase around the 40th day. Days as individuals become sick, it reaches its highest point on the 80 days and then begin to decrease as individuals recover. Indicators of the intensity of the epidemic include the peak height and length of the outbreak. As patients begin to recover from the sickness, the recovered curve begins at a low point and steadily climbs until it reaches a high point of the 40-day mark. Its ultimate level provides information on the percentage of the population that is immune following the epidemic. For conclusion, the susceptible infectious recovery SIR model is a useful tool for understanding and forecast influenza transmission dynamics within population. It captures key components of the disease life cycle and can be tailored to include specific factors like transmission and recovery rates. However, difficulty exists in describing influenza dynamics, such as individual level interaction, regional variability, and changing data sources. Future research should focus on fine-tuning the model and collaborating among epidemiologists, modelers, and data scientists. Thank you.